Hey guys, in this video I will discuss about alternating series and absolute convergence. So as usual, we will start with some recall of the things that we have discussed so far. So first, the definition, it says that the series AN converges if its sequence of partial sums Sk is convergent. So let me rewrite again what Sk is. So Sk is the sum of the first k terms of the series. If the sequence of partial sums does not converge, then we say that the series diverges. Then we have the divergence test. It means that if the limit of an as n approaches infinity is not equal to 0, then the series AN is divergent. So if the tail of your series does not go to 0, then the series is divergent. So again, this is a test for divergence. You cannot use this to show that a series is convergent. And then we have the integral test. So here we consider the series AN with non-negative terms. And suppose we have a function f that is continuous, positive, decreasing in the interval 1, infinity, and the value of the function at every positive integer n is equal to the term an. Then, the series converges if the improper integral of f of x dx from 1 to plus infinity converges, and the series diverges if the improper integral of f of x dx from 1 to infinity diverges. Now, like what I have mentioned before, it is possible that your interval does not start at 1. So, for example, if your terms are something like this, so it's not completely decreasing, but at some point, the terms of your series eventually decreases, then you can start at the point where the terms of the series started decreasing. So, for example, this is at point k, then you can start the interval at k. So, the improper integral becomes the integral from k up to plus infinity of f of x dx. Okay, so again, what we want to make sure is that this function f is continuous and positive at some point towards this direction. I mean, at the tail part. Okay, it is decreasing starting from that k, and definitely you want your function to be equal to an for each n. So starting from a n equals 1. Okay, so this is our integral test. Then last time we had comparison tests. So first, the comparison test, or in some references, they call this the direct comparison test. So they label this as DCT. So in here, suppose we have two series, AN and series BN, and they have non-negative terms. And suppose that for each n, AN is less than or equal to BN, and that the series BN is convergent. The conclusion is that the series AN is also convergent. So if there is a series and some series bigger than that original series is already convergent, then the original series is forced to be convergent. Again, we are assuming that the series have non-negative terms, so that if you look at the sequence of partial sums, particularly of the lower part, it just increases. So basically, the sequence of partial sums of the lower series is increasing and bounded above by the other series. So the sequence of partial sum will be convergent. And the second statement for DCT is that when your AN is greater than or equal to BN, and that Bn is divergent, the sum Bn is divergent, then the sum An is also divergent. So if you look at this, it is the sum Bn that is smaller than the sum An. Look at this. Bn is less than or equal to An, or An is greater than or equal to Bn. Okay? Since the terms of your Bn are non-negative, then these are all positive. I mean, the sequence of partial sums are also non-negative. Particularly, they are, possibly positive. And this is divergent, so the sum Bn will just go to plus infinity. So if the smaller series is going to positive infinity already, then the bigger series will definitely go to positive infinity. Hence, we have the bigger series to be divergent. So this is the direct comparison test. And then there's another comparison test. We call it the limit comparison test. So here we have two series, AN and BN, with positive terms. Okay? In here, we don't need the comparison AN less than or equal to BN or AN greater than or equal to BN. We just want to take the ratio AN over BN, and we'll get the limit as n approaches infinity. If the limit is a constant, a positive constant, then both of this series converge, or both of them diverge, meaning they have the same conclusion in terms of convergence or divergence. Okay? Now, as a remark, you have to know some series. I mean, at least you know if it is convergent or divergent. So it will be helpful if you remember this type of series. So one of them is the geometric series. Another one is the P series. But of course, you can use other series that are not geometric or not P series. But you need to identify whether that series is convergent or divergent. So you will need the conclusion for that series in order to use it for your comparison test or limit comparison test. So now, what I'm going to do is define another type of series. So here, we have an alternating series. So it is a series whose terms are alternately positive and negative. Okay? So the terms alternate in signs. So it will be of the form sum from n equals 1 to plus infinity of negative 1 to the n bn, or sum from n equals 1 to plus infinity of negative 1 to the n minus 1 bn, where bn is positive for all n. So this power here, or this power here, makes the series alternating. The difference between the two, here you start with a term, positive term, while this one you start with a negative term. Start negative term. Okay? So some examples, we have here negative 1 to the n times n, and you sum up from n equals 1 to plus infinity. Since here it is n as a power of negative 1, and you start with n equals 1, the starting number is a negative number. So minus 1 plus 2 minus 3 plus 4 minus 5 plus 6 and so on and so forth. Also, we have this. We have sum of negative 1 raised to n minus 1 over n. You start with n equals 1, but the power of negative 1 is n minus 1. So you will start with a positive number. So in here, you will have 1 minus 1 half plus 1 third minus 1 fourth plus 1 fifth and so on and so forth. So we call this the alternating harmonic series. As you can see, it's just a harmonic series, 1, 1 half, 1 third, 1 fourth, blah, blah, blah. But the signs are alternating. So alternating harmonic series. Now, in order to determine whether an alternating series is convergent or divergent, there is a very simple way. We call this the alternating series test. So here, alternating series test. So what is this? You are given an alternating series. So let us just write it, either this one here, Bn, n equals 1 to plus infinity, or some negative 1 to the n minus 1, Bn, n equals 1 to plus infinity, where here Bn is greater than or equal to 0 for all n. So in here, if the sequence Bn is decreasing, meaning Bn plus 1 less than or equal to Bn, and the limit of Bn as n approaches infinity is equal to 0, then the series is convergent. Very easy to use, but it's limited for alternating series only. Okay? So again, you got an alternating series where the positive, if you get the positive terms, or you say you get the absolute values of the terms are the bn's, okay? If that sequence is decreasing and goes to 0, then the series is convergent. Take note, in our usual notation, we have the series AN. The AN here is this entire thing. Okay? Just to be clear. So anyway, let us use this alternating series test. So for example, the alternating harmonic series. Here, your bn's, this is actually 1 over n. Okay? So this is the one that makes this alternating, but this one here, you got your 1 over n. And we know that this one, first thing, as n increases, 1 over n decreases. Or you can prove this using this thing. Okay, bn plus 1 less than or equal to bn. What we know is that your n is less than or, well, less than n plus 1. So if you get the reciprocals, you will have 1 over n plus 1 less than 1 over n. And this is precisely your bn plus 1 less than bn. So decreasing. Number 2, obviously, you got the limit of 1 over n as n approaches infinity. This is equal to 0. So, by alternating series test, the series negative 1 to the n minus 1 over n, and from 1 to plus infinity is convergent. Okay. Next, determine whether the alternating series, -1 to the n squared over n squared plus 1 converges or diverges. So for this one, we have an alternating series, but we actually don't need to use the alternating series test. Okay, so look at this. Um, Here, let us write our bn's. The bn's, this is equal to n squared over n squared plus 1. If you look at the second condition, you want the limit of bn to go to 0. But in here, if you look at this, limit of n squared over n squared plus 1, as n approaches infinity, this is equal to 1. So it already fails the second condition so that you can use your alternating series test. So it means you cannot actually use the alternating series test because one of the hypotheses already fails. However, we have a limit of n squared over n squared plus 1 that is equal to 1, which means definitely you will have the limit as n approaches infinity of -1 to the n squared over n squared plus 1, this is not equal to 0. In fact, in fact, for even n, the limit is equal to 1, but for odd n, limit is -1. So the limit is not equal to 0. So you can actually just use the divergence test. By divergence test, the series -1 to the n squared over n squared plus 1 is divergent. Okay? So that's our alternating series and the alternating series test. Now, let me define what we call absolute convergence. So in here, a series AN is said to be absolutely convergent if the series of absolute values is convergent. So again, the series sum an is absolutely convergent if the series of absolute values sum absolute value of an is convergent. So in here, your original series, you just have sum of an, and then you consider the absolute values of an, and then you add those absolute values. Then you study this series. If this series is convergent, then the original series, we say it is absolutely convergent. Now, suppose the original series is convergent, but if you put the absolute values, it is divergent. Then we say that the original series is conditionally convergent. Again, you got the original series, sum of an, and you know it is convergent. But if you put the absolute values for your terms an, the new series is divergent. Then we just say that the series an is conditionally convergent. Right? Now, as a theorem, if we know that the series AN is absolutely convergent, this means that the sum AN here is convergent. Okay? So the series AN is absolutely convergent. It means the sum absolute value of AN is convergent. Then this original series here, it is automatically convergent. Okay? So again, you got the original series sum AN. It is absolutely convergent. Then that series must be convergent. Okay? So first, let us, differentiate what it means to be absolutely convergent and conditionally convergent using some examples. For example, we consider the sum -1 to the n minus 1 over n squared. It is written here that this is absolutely convergent. Why? This is your original series. Now we take the sum absolute value of -1 to the n minus 1 over n squared, and from 1 to plus infinity. But the absolute value of -1 to the to some power, it's just +1. So this one here, this is 1 over n squared, and from 1 up to plus infinity. And this is a what? P series. P equals 2, which is greater than 1. And this is convergent. So the sum with the absolute values is convergent. So if you remove the absolute values, you will get the original series. We say it is absolutely convergent. Second example here, the alternating harmonic series, it is just conditionally convergent. We have already shown in a previous example just earlier that this one here is convergent using alternating series test. But if we take the absolute value of -1 to the n minus 1 over n, this is just the harmonic series, sum 1 over n. And we know that this is divergent. So the original series, it is convergent using alternating series test. But if you put the absolute values, becomes a divergent series. So the original series is conditionally convergent. Okay? Now, because this series here is absolutely convergent, this means that the series -1 to the n minus 1 over n squared is convergent. It is an alternating series. You can prove using alternating series test. But there will be times when your series is not alternating, but you were able to show that it is absolutely convergent, then you can conclude that the original series is convergent. Let us illustrate that using some examples. Um, Let us see first, determine whether the series -1 to the n arctan n over n cubed minus 1 converges or diverges. Now let us look at this. We can start with your Bn. This is what? Arctan of n over n cubed minus 1. You need to show that this is decreasing and the limit goes to 0. And if you can do that, because this is alternating series, then you can use alternating series test. However, this arctan here, this is an increasing function. The denominator here, this is also increasing. So numerator increasing, denominator increasing. It's not straightforward to show if your sequence is increasing or decreasing. So you have to find a way. Okay? So one way is, well, you have your f of x equals arctan of x divided by x cubed minus 1, and then show that this is decreasing. Just show that this is a decreasing function using first derivative test. It may be tedious. Okay? Show this is decreasing. Show this is decreasing. And then the other one, well, maybe it's easy to show that Bn, this is equal to 0. I mean, limit of Bn is equal to 0. But again, like what I said, this is tedious, particularly the first one. So what we're gonna do is to use the fact that if the series is absolutely convergent, then it is convergent. So in the solution that I will show you, this will be a chain of, using convergence test. So let us look at this one here. We will consider, solution. Let me put this as a solution. Consider the sum absolute value of negative 1 to the n arctan of n over n cubed minus 1. But this is just the sum of arctan of n over n cubed minus 1. And here we are starting with n equals to plus infinity. Okay? That's our first step. What we're going to do is to show that this is increasing. Oh, sorry. What we're going to do is to show that this is convergent. And hence, this thing here without the absolute value, particularly this one here, will be absolutely convergent. And therefore, we can conclude that it is convergent. But in order to show that this is convergent, what we're gonna do is to use the fact that for all n greater than or equal to 1, your arctan of n, this is less than or equal to pi over 2. In fact, it is strictly less than. So let us put that strictly less than. Which means that arctan of n over n cubed minus 1, this will be less than pi over 2 over n cubed minus 1. Furthermore, this is what we have. Also, your n cubed minus 1, oh, not this one, not this one. From this inequality, we will now consider the sum pi over 2, 1 over n cubed minus 1. But this one here, we can compare with sum pi over 2 over n cubed. Pi over 2 sum of 1 over n cubed. And this is convergent P series, P series, P equals 3 greater than 1. Right? Convergent P series. Then we take the limit. We take the limit of what? Pi over 2 over n cubed minus 1 times n cubed over pi over 2, and this is equal to 1 as n approaches infinity. So this one here, our an, this one here, and including, well, this one, let me put this one, this is our bn. So we are taking the limit of an over bn. We are finding the limit of an over bn. And it is equal to 1, which means, so by limit comparison test, the series pi over 2 times 1 over n cubed minus 1 is convergent. But then again, we now have this series to be convergent, and we use this series to compare it to this series. And we have less than here. So something bigger is convergent, then this is forced to be convergent by direct comparison test. The series are tan of n over n cubed minus 1 is convergent. But this series is this thing here. So, by definition, the series negative 1 to the negative 1 to the n minus 1, or just to the n, of arctan over n cubed minus 1 is absolutely convergent. And so, it is convergent. Okay? So, we now have our conclusion. The series converges. So now take a look on how we did it. We started, considering the absolute value. So we are looking to show that the series is absolutely convergent. That was this part here. But in order to show that this one is absolutely convergent or this one is convergent, we tried to use comparison tests. On the other hand, this one, if we want to know if this is convergent, this is not somehow straightforward. We needed to pass to the limit comparison test. We got denominator n cubed minus 1, and we take out that negative 1 so that we'll just have the denominator n cubed. which is a p-series. So we needed to pass the limit comparison test. So now, this is the last thing that we have to consider. We now move backwards. By limit comparison test, this one here with the summation will be convergent. But then we are using this to directly compare it with this original series. No, not the original series, but with this series. So by direct comparison test, we now know that this is convergent. But this one here is just the absolute values of the original terms of your series. So without the absolute values, it is absolutely convergent, and therefore it is convergent. So in a lot of series problems, you may need to use several series tests just to conclude that your main problem is convergent or divergent. Next, show that this series sine n over n squared converges. So we know that this is convergent. We just need to show the solutions. So for this one, what we're gonna do is to consider the series with the absolute values. Take note that your sine n, as your n runs through positive integers, the value will be less than or equal to 1. Take note, sine n, this is less than or equal to 1, but greater than or equal to negative 1. In absolute values, the absolute value of sine n will be less than or equal to 1. It's not just 1 or negative 1. No. It could be any number between negative 1 and positive 1. So what we're going to do is to show that this is actually absolutely convergent. So we take the absolute values. But then, because we have this, so since absolute value of sine n is less than or equal to 1, we have absolute value of sine n over n squared. This will be less than or equal to 1 over n squared. So now we consider the series 1 over n squared, which is a convergent p series. Again, we have been using this series here. So let us just write it over and over again. This means, so the series absolute value of sine n over n squared is convergent, and hence, without the absolute value, series sine n over n squared, this is absolutely convergent. Therefore, it is convergent. The sum sine n over n squared is convergent. Okay? Let me just complete the reasoning here. This this one here is a convergent P series. So this one is convergent by, let me just write it, by DCT, direct comparison test, because, well, you compare these two guys here. And hence, this series is absolutely convergent. Right? Now let's have this. Determine whether the series is convergent or divergent. We have the sum cosine pi n over 3n minus 1 raised to 1 over 5. So we are only interested whether this series is convergent or divergent. Now, if you look at this, cosine pi n, so pi n runs from 1 to plus infinity through integers. So this is just pi, 2 pi, 3 pi, 4 pi. You can rewrite cosine pi n as negative 1 to the n, and starting from 1 up to plus infinity. So in here, cosine pi n over 3n minus 1 raised to 1 over 5. This is negative 1 to the n, or sum from 1 to plus infinity of negative 1 to the n over 3n minus 1 raised to 1 over 5. Power is n because you start with n equals 1, then you will have your cosine pi. And cosine pi is negative 1. So n equals 1, we have negative 1 as the first term. So this is actually an alternating series. And the terms of the series is simple. In fact, you can just write Bn as 1 over 3n minus 1 raised to 1 over 5. And in here, they are all positive because your n starts with 1. In here, as n increases, the expression 3n minus 1 raised to 1 over 5 also increases. So, 1 over 3n minus 1 raised to 1 over 5 decreases. So, we accept that one. If the denominator increases while the numerator remains constant, then the fraction actually decreases. 2, also, limit of Bn as n approaches infinity, well, this is obviously 0. If it's not obvious, you have to compute it. But we'll accept that one. So, by alternating series test, the series cosine pi n over n, or 3n minus 1 raised to 1 over 5, and from 1 to plus infinity is convergent. Okay? So, I will stop at this example, and I want you to work on the next examples that we have in here. We have this series, and then we have, oh, I want to add another estimation theorem. If you remember, When we discuss integral tests, there is an estimation theorem towards the end that is related to the improper integral or the integral test. So in here, we have another estimation theorem that is related to the alternating series. So here we let S to be the sum of the alternating series. And since this is an alternating series, we have your Bn to be greater than or to be positive. The Bn must be decreasing and the limit is equal to 0. Then for each n, the error term, Rn, will be less than or equal to Bn plus 1. So again, what is this Rn? You got your Sn equals A1 plus A2 plus dot 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 plus An. So Rn, this is S minus Sn. So this is equal to An plus 1 plus An plus 2 plus dot dot dot. The tail, the sum of the tail of your terms. So the alternating series estimation theorem says that this one here, this guy here in absolute values will be less than or equal to that Bn plus 1 to a single term. Take note, Bn plus 1, it's this part here. And your Ans, again, it's the whole thing. That's with the negative 1 to the n. So that is your An. So, how do we use this? Find the sum of the series correct to 3 decimal places. Series is negative 1 to the n over n factorial. And we want this to be correct up to 3 decimal places. So, to solve this, so we want to find n such that the error term in absolute value correct to 3 decimal places, that means you got 3 zeros after the decimal point. And even if you round up, you have your 0.5, you will still have a correct 3 decimal places. So you want this one here, your absolute value of Rn, to be less than 0.0005. Correct to 3 decimal places. Okay? 0.0005. Why? If you look at this, your Rn could be, in absolute value, could be 0.0004. And if you round this number, this won't change. This is still 000. On the other hand, if your absolute value of Rn is equal to 0.0005, if you round this number, this will go to 0.001. So the third decimal place here changed. It will add that 1 in your actual sum. So you want your absolute value of Rn to be strictly less than. Here, you got here 499 doesn't really matter. If you round this off, this is still 0.000. I mean, 3 zeros, correct? Because this is 4. So this is what we want. You want your absolute value of Rn to be 0 to be less than 0.0005. But we know, so from the previous theorem, absolute value of Rn is less than or equal to Bn plus 1. So so if Bn plus 1 is less than 0.0005, then this inequality will hold. Then absolute value of Rn will be less than 0.0005. Okay? Now, what is Bn? Bn is 1. So now Bn is equal to 1 over n factorial, which means that, so Bn plus 1, this is equal to 1 over n plus 1 factorial, and you want this to be less than or equal to 0.0005. But anyway, 0.0005, this is equal to 5 divided by 10,000, correct? So here, 1, 2, 3, 4. So you need 4 zeros. But 5 over 10,000, this is what? 1 over, let us see, this is 1 over 2,000. 1 over 2,000. So, what does this mean? So, we have your n plus 1 factorial. This must be greater than or equal to 2,000. So, we'll try to find the smallest n such that n plus 1 factorial is already greater than 2,000. So, in order to do that, well, we can just have, let us see some numbers. Say, so by substitution, we will have, say, 7 factorial. What is 7 factorial? 7 factorial is 5,040. It's way big. 6 factorial. 6 factorial is 720. So we cannot take 6 factorial because it is 720 only, and we want something that is greater than 2,000. Therefore, we take the 7 factorial. So n plus 1, this is equal to 7, or that your n is equal to 6. Okay? So we can verify, you try to verify that this is indeed correct. So to verify, let us just put a single note in here. Single note here. Try to get the value of sum n equals 0 to plus infinity of negative 1 to the n over n factorial. And then you try to get from n equals 0 up to 6. You also try to get some n equals 0 up to 7. And say let's take the sum n equals 0 up to 5, n minus 1 to the n over n factorial. Then you get the difference between this sum here minus each of this. And you check which one, so 5, 6, or 7, what is the smallest number that will satisfy this condition. Okay? So that ends this lecture video's discussion. So, yep. See you when I see you.